Alright, my name is Collin Korey, and I'll be doing a hopefully quick and concise explanation of left-turning tendencies here. So I've got a little Model T-37 aircraft, and unfortunately that's a jet aircraft and not a prop aircraft, and so I'll use this piece of foil here as my visual training aid for the propeller. So I think it's going to be important to break down what are left-turning tendencies. Left-turning tendencies are it is the tendency of the aircraft to want to yaw to the left as a result of different aerodynamic factors and effects on the aircraft in different stages of flight. So it's probably best to start with what contributes to left turning tendencies. You have four main ones. You have your P factor, that's caused by the propeller. You have your torque effect, also caused by the propeller, the force the propeller spinning. You have your spiraling slipstream, yet again the propeller, and then the gyroscopic precession, and yet again that is also from the propeller. So really, the propeller is the cause for all these tendencies of the aircraft to want to yaw to the left. So we'll go and break down now what the direct cause is for each of these different tendencies. Starting with P factor, since I think it's one of the more complicated topics. Hopefully this piece of foil can be a good visual aid. But the reason for P factor, to start from the beginning, is it's due to the twisting of the blade. Now, the manufacturer doesn't twist the blade just for fun or because it looks flashy. They do it because they want to create equal thrust with every revolution throughout the entire propeller, from this end to this end. Now you have to think towards the center of the prop. If you go from here out to this area, with each revolution, the center of the prop is doing the same amount of revolutions per minute as the outside of the blade, yet the outside is longer. And so it only makes sense that in order for the outside here to do the same revolutions as the inner parts of the blade, it has to actually rotate faster. And because of that faster rotation, what would happen is you'd be creating unequal thrust with every revolution if the propeller were just flattened and not twisted there. And so what the manufacturer does is they twist the blade angle in a way kind of like this. So now that that blade angle is twisted, and let me just try to shape this a little bit better. Yeah, we'll say something like that. I think that's pretty accurate. Maybe a little bit excessive, but it'll do the trick for this. So they twist this blade here so that now with each revolution, the propeller is drawing an equal amount of thrust throughout the entire blade. There. You're not getting more on the outside, less on the inside, and vice versa. So due to that twisting and how they plan out for this twisting, the angle that they twist it at is the angle that the propeller will be the most effective during the cruise phase. And so what that means is when the airplane is relatively straight and level, not a very different angle of attack, the nose is just going straight there into the relative wind, the propeller is twisted so that equal thrust is found throughout the entire revolution. But as you change blade angles, what happens is due to the twisting, now the descending side here has a high angle of attack, and the ascending side with each increase in pitch up actually becomes flatter and flatter. So now you can kind of see this a little bit better as I twist this up. You can see this one here has really big angle of attack, whereas this side here, the left ascending side, is going to be relatively flatter to the relative wind. And what this causes is this side having a higher angle of attack on the downward motion, this side with a high pitch attitude having a lower angle of attack with the up motion, creates an asymmetry of thrust. Essentially, this side is now creating more thrust, this side is creating less. And keep in mind, this is with the higher pitch angle of attack. And that only increases the more and more we pitch up until we exceed our critical angle of attack with the aircraft itself and reach a stall. So the more we pitch up, the more asymmetric thrust we're getting now. More on the downside, less on the uplifting side here. And what that creates is more of a thrust moment here, less here, and so you're going to get more of a moment here, and what do you know? More moment on the left side with more thrust being created here, wants to yaw that nose there to the left. So that is why P factor is an effect we deal with. Now, key takeaways from that. The cause of P factor, you're not really going to find a left turning tendency in straight and level flight. It's as you increase pitch up that you're going to find that tendency. Now keep in mind, if we were to have a really large pitch down moment, the exact inverse would happen. You'd have a rotation here, and the down sweeping side, I'm doing this the opposite way, the down sweeping side here is actually going to get flatter and flatter as the nose pitches down more, and the ascending side will actually get a higher angle of attack. It'll go more into the wind, therefore creating more thrust, and so you'd actually be getting more of a thrust moment here and a big downward pitch moment, and less thrust on the descending side, and so you'd actually get the inverse. You get a yaw to the right. But you have to think that when we're descending, we're never really pitching down that crazy of an amount. And also, often in descents, we are at a low power setting. And so that's also a contributing factor. The more power you have in there, the more RPMs that prop's doing, the more asymmetry, the more revolutions there are for asymmetric thrust generated. So in climbs, it makes sense that we'd experience this a lot. But in descents, the opposite would happen. It's just never really something that we deal with too much because, again, we're not descending with a high power setting and too crazy of a negative angle of attack. Now, to get into torque effect, this one is pretty quick or easy to explain. There's not a whole lot you have to understand with it. Referencing Newton's third law, you have an equal and opposite reaction with every action. And so the prop itself, if you're in the cockpit here looking out, it's going to go clockwise. Your downside is on the right, your ascending side is on the left here. So torque effect, the prop is spinning clockwise, and as that happens, you actually get a yaw, an equal and opposite reaction to the left, which creates a yawing moment there. So as the propeller is rotating here in this clockwise motion, we're getting a counterclockwise motion, which, as you would guess, here is equal and opposite to that and going to yaw our nose to the left. We have our spiraling slipstream. Now, as our propeller rotates and attacks some air and creates our forward lift, our thrust, that's actually, it's propelling air backwards. And how it does this is kind of in a similar way that the propeller rotates. It creates a corkscrew pattern of air swirling around, rotating, and what happens is, as that propeller goes down, it creates this corkscrew effect, and as that swings around, it eventually contacts our vertical stabilizer, or stabilizing surface there, which is where our rudder is mounted, but it's not so much that it hits the rudder, it just hits the entire vertical stabilizer. And so as we get that corkscrew motion here from this angle, it's going to rotate around. It's going to hit here on the left side, which creates a force pushing this way. And so you think, oh, if it hits the left side, why would it yaw to the left? Well, it's creating the force here, and that caused that nose to want to swing in this direction there. So spiraling slipstream, that's also in direct correlation to our power setting. The faster the RPM, the propeller spinning, the higher revolution per minute it has, the greater amount of slipstream going and hitting that vertical surface. Finally, we have our gyroscopic precession. Now, I won't go too heavy into this since this is a topic on the left turning tendencies of an aircraft, but a gyroscope operates on two principles. What it is it's something that rotates fast enough that the fast rotation creates rigidity. You can think a bike tire. As you hop on the bike and you start pedaling, you're really wobbly and unbalanced. But as you begin pedaling faster and faster, as those wheels gain more revolutions per minute, you begin getting more stable and can eventually ride the bike, with no hands. If you're so talented, I'm unfortunately not. But the same principle applies with the propeller here. As it's rotating at very high speeds, and what actually happens is it not only gains rigidity, which really isn't the point of this whole thing, but it also experiences precession. Any object acting like a gyroscope faces precession, which means that if a force is applied as that gyroscope is rotating, the force is actually felt due to the high rotation speed. It's actually felt 90 degrees later in the forward motion of where the force was applied. So in a more simple way, if this propeller is spinning and rotating this way, if I enact a force here at the top and it's rotating here clockwise, if I enact this force here at the top, that's actually not going to be felt here. The plane isn't going to pitch up due to that force there. Or technically, this would be a pulling motion, so it wouldn't nose down. It'll actually go to the right, and 90 degrees later here in this angle, that force that I imposed there on the back of the prop is actually going to be felt here, and so that's going to cause the nose to be out to the left. Now, the reason I use that example, applying the force here behind the prop since it pulls forward, applying that force here to the top and having it come down to the right and cause a left turning tendency is because this is really where you'll find the gyroscopic precession happening is in a tailwheel aircraft, really during takeoff. So if you're flying a tailwheel aircraft, it's a little bit different. You actually get up to your rotation speed, and then instead of initially pitching up, as you gain speed, you actually pitch down to get the tail off the ground. And what happens is the propeller is rotating, and by giving that pitch down, what happens is a force is actually felt on the prop here. That angles down to the right, causing this moment here on the left, and you get a left turning tendency in tailwheel aircraft due to that. So that one we don't experience really profoundly in conventional tricycle gear. But gyroscopic precession is still a factor worth considering when you're talking about left turning tendencies. Now, just to wrap it all up, I know I'm going a little over time here, but what I like to teach my students is we go and do this work on the ground and understand the left turning tendencies because they truly will make you a better and safer pilot. In our trainer aircraft, our 172s or our Cherokees and Archers, we have low performance, low power engines. We're not really getting the huge mind-blowing effect of these left turning tendencies in the same way that we would if we were to go into a high performance aircraft, something with more horsepower, and go experience it in that sense. So while you might not, you're always going to be told more right rudder by your instructor when you're initially doing your training. And what I like to tell my students is that really get used to that and listen to that. And eventually your mind should be tied to any application of power, increase in power, or any changes in pitch up, tie that to an increase in need for right rudder. Because in our trainer aircraft, we're not so worried about losing control. Our engine doesn't give us that amount of performance where one little slip up and we're going to instantly yaw to the left and get into a stall spin scenario. That's not so much the case. But as you move up in your careers and get into these more capable aircraft, you are going to really need to take that into account and really have the application of right rudder there tied into your muscle memory of applying power or increasing your pitch up. Because with those high performance aircraft, you very can find yourself in a situation where you neglect to input that need for right rudder, account for left turning tendency, and before you know it, your nose is yawing to the left, you're finding yourself in an unusual attitude, pitched up, and yep, there you go. You find yourself in a stall spin accident, or at the very least, a brief moment of real uncomfortability there. So that's my explanation there on the left turning tendencies of an aircraft, the 4 factors that we really experience and that contribute to those left turning tendencies. Thanks.